Okay, so I want to go over an example now, which is a pretty tricky region to deal with. It's not as straightforward as the last one, where you basically just had one like um one function for a bound and then everything else was like a constant. Here we have multiple functions defining this region. So you can see I've drawn it out here. And again, this is from the OpenStax Calc 3 textbook if you want a better drawing or to see how they did it. But the line up here, the curve up here, I should say, is y equals x plus 2 squared. Okay, that's right here, this part. The big curve that really defines the right side of this area is x equals y minus 1/16 y cubed. And of course, we could define that in terms of x if we want to. It's not going to be a function, right, of x. So something we might need to be careful about. And then this is just a line right here, and this is just a line right here. All the tick marks are just one length. So like this point is 0, -4. This point is -2, 0, which would make this point -2, -4. Okay. And then that top point is 4, 0. Or 0, 4 rather. So we basically want to kind of break this equation up into pieces, or this area up into pieces. And by the way, the function we even want to integrate in the first place, so we call this region D. Okay. And we want to integrate the function 2x plus 5y. Okay. So not too complicated of a function, at least. It's really the area that we're integrating over that's the complicated part of this one. So the idea is we can kind of break this up into, we can break it up into as many pieces as we need to, but there's kind of three natural cutting points here. So the first region to look at would be this region right here, bounded by the y-axis and the top part of this function up here. Okay. Then right next to it would be another region, right, bounded by y equals x plus 2 squared, and again the y-axis. And then this bottom region would also be kind of a natural breaking point. So here this is just bounded by a vertical line, just like, you know, how the y-axis is a vertical line, so it'll be the same kind of idea. And the bottom part of this function up here. So it might be helpful to kind of give these some names, because if we're decomposing it, we're going to have to break up the integral using the decomposition into different sets. Okay, so if we call this light blue part D1, it might help to write out exactly what this region is. This isn't 100% necessary. You could just read it from the picture if you're comfortable with that, but you know, of course, writing out as much as possible is always helpful. So x is between -2 and, or I'm sorry, I'm looking at the wrong one. That would be for D2. So if we call this one D1, let me rearrange this here. So the y part is what's constant, right, between 0 and 4. Okay. And then x is defined via a function. Of course, you can flip that around, but it's probably going to be pretty complicated to do that just at first glance. Like whenever, because we have that y cubed and a different y like separately, it'll probably be pretty hard to get x by itself. Maybe not impossible, but I think it would definitely be tricky. So let's try to not do that if we can. So x then is going to be between 0 and whatever that function is, though. So 0 less than or equal to x, less than or equal to y minus 1/16 y cubed. Okay. So then D2 was the one I started to write out. Okay, so that one, x is going to be between -2 and 0. Oops. Okay, and then y is going to be defined by this function. So it's going to be bounded by by 0, and then whatever value this function is at whatever point. Okay. And then finally, we'll call this last one D3. Okay, so this one, the x value, well, let's write the y value first, since that's just a constant. Now the y value is going to go from -4 to 0. Okay. Now the x value, we want to go left to right. So it's going to start at -2. And then it's going to go, so starting right here, right at -2. And then it's going to whatever the point is on that function again. Okay. So then, of course, you don't have to write it out, but you should just note that du is equal to d1 union d2 union d3. So we can break this integral up over these 3 regions here. Okay. So the integral of d over d of 2x plus 5y dA would be equal to d1's integral. So this is going to be 0 to 4. And then 0 to y minus 1/16 y cubed. And we're kind of just hoping that we don't need to bother changing any of these bounds here. Like I said, the function is pretty simple, right? This is just a very simple linear function, not even any constants on it, on the end or anything like that. So it should be very straightforward to integrate, so we shouldn't need to even worry about the bounds at all. It really only comes up like when you're dealing with more complicated functions like the e exponential function, where some of them are not integrable, or some of them need integration by parts or whatever. But with a linear function, it shouldn't matter. Okay, so that was d1. d2, we're going from -2 to 0, and then from 0 to x plus 2 squared. I'm not going to bother expanding that out until I see a reason to. So this is going to be dy dx. And then the last region, d3, that one's going from -4 to 0 on the y's. And hopefully it's clear by now that like you want to do the variable bounds as your first integral, because then you'll end up with something, as just a number rather than having a variable in it. And also geometrically, that's what makes sense to do. Like I said, you kind of define the region first and then you fill it in. But even without taking that into account, just the math isn't really going to work out if you do it the other direction, without changing the bound. So anyway, so -4 to 0, and then -2 to y minus 1/16 y cubed, 2x plus 5y, and that's going to be d x dy. So again, the hard part is really just setting up the integral. Now it's just kind of grinding it out. So I'll go ahead and do it. I'll kind of just skip over some of the finer details here, and just insert what the answer should be, because again, it's just kind of just tedious at this point, right? It's just setting it up that's the big part. So that first one, we got 0 to 4 of, that's going to be x squared plus 5xy, and we're going from x equals 0 to x equals y minus 1/16 y cubed. And maybe it's helpful just to like give these names and do them like one at a time. Okay, so let's call that one 1, that one 2, this one 3. Okay, so we'll say that 1 is equal to this. So anyway, so this is going to be 0 to 4. And then we're going to plug that in for x. So this is where it gets kind of tedious, but it's nothing we can't handle. Plus 5 y minus 1/16 y cubed times y. And then the rest of it will just be 0. Okay. So we'll go ahead and just grind it out. You basically have to just multiply everything out. There's not really a shorter way to do it that I can see, any kind of substitution. So let's go y squared minus 1/8 y to the 4th plus 1/256 y to the 6th plus 5y squared minus 5/16 y to the 4th. Okay. So yeah, so then you just grind this one out. So dy now. So I'll just write what the answer is for this one, which it looks like is 1664 over 35. Okay. And I wouldn't give you one that's like this tedious on a quiz or a test. I mean, I would, there might be some that require some algebra, but I think this one is just like a little too much to where you're spending way more time doing algebra than you are doing multivariable calculus, right? So that's why I'm not going to bother just like writing the entire thing out here. If I were to give you this kind of problem, like specifically with a region this complicated where you need to break it into different parts, I would just ask you to set up the integral. There might be some tedious ones that you got to grind out, because you do need to put that algebra to use, get that practice in, because that is stuff that will come up in statistics in general is, it can be very tedious doing a lot of those calculations, and of course you do a lot of them in a computer program, but still it's something we need to be comfortable with. But for this one, I think the main focus is setting up the region here, so I would just ask you to set it up. But anyway, so I guess I'll just kind of write out what the answer is with that in mind, since I already did I did like half of the first one. The rest of them are all going to work exactly the same, right? So this first one, it looks like you get 40/3. And the third one, it looks like you get negative 1696 over 35. Okay. So then ultimately, when you add those together, you will get 1304 over 105. Yeah, so again, not promising that there won't be any where like you have to FOIL, you have to do algebra. That can get a little tedious, but nothing like this tedious. I think this is a little too much, where you have 3 double integrals and you have to do a lot of algebra on all of them. So here, the focus would be the main setup of the problem.